Jnanam Paramam Dheyam. Knowledge is supreme.
Okay, what was the next one? We had a Hamilton's equation in classical mechanics. Similarly, we need to give a time evolution of the state vectors. So, there is an equation which is your familiar time dependent Schrodinger equation, and that Schrodinger equation again depends on Hamiltonian. Here it will be an operator. So, this is an operator equation operating on any state vector psi, and this equation will tell us how the state vector psi evolves in time. Okay, so that is where the dynamics is coming up, time evolution of the state psi. Suppose the Hamiltonian is kinetic energy plus potential energy, and you putting potential energy like harmonic oscillator or hydrogen atom, they are all called time independent potential energy. You know when you will get time dependent potential energy? You can start having, time dependent electric field on a charged particle, then the potential energy will be actually time dependent, right? But we are not going to consider that, at least for this course. In this course, your Hamiltonian which we are going to take is always time independent. So, this is a very simple thing. If the operator is independent of time, you can take all the things on one side. So, this will give you a log function, and then this will give you a IHT, and you will have some constant, and you can solve it and get this equation. Psi is H operator on psi, and if you take V to be only a function of x and p, V also in general is an operator, and of course kinetic energy operator is p squared over 2m. Hamiltonian will be T plus V. So, in such cases I can write IH cross del psi by psi to be integral of H hat T dt. H is independent of time, I can pull it out and go from T naught to T, and that will give you H T T minus T naught. What is this? Left hand side? Left hand side is log function of psi. Psi h cross log psi is h hat t minus t naught, and take the exponential on both sides, and then you will get, so we have IH cross del by del, IH cross del psi by psi equal to H t minus t naught. Psi h cross log psi is H t minus t naught. Psi as a function of time will be e to the power of minus I h t minus t naught by h cross times some constant, and you have to make sure that at t equal to t naught, the left hand side should match with the right hand side. Is that right? So, at t equal to t naught, this term vanishes, this is an identity operator. So, psi t naught will be psi t naught. and this gives you the state vector, initial state vector at t naught evolves in time by this operator to give you the new state. What was Hamilton's equations doing? Hamilton's equation was only looking at the evolution equations in the phase space. But here in quantum mechanics, we say that the information about the system is contained in the ket vector psi, and we are interested in the time evolution of that ket vector psi, and the time evolution is given by this operator, and this operator is known as the time evolution operator. So, let us call that as time evolution operator. What are the properties of it? What are the properties of it? So, let me call this also the time evolution operator. Formally people write it as u of t comma t naught. So, what are the properties? U of t naught comma t naught is identity operator, and you can also see some more other properties. What will be the, if you go from t naught to t, this is the operator. If you go from t to t naught, it becomes the inverse of the operator, and you can show some of the properties, and those properties will tell you what is the nature of this time evolution operator. That this is the Schrodinger equation which gives you the evolution of the state vector, depends on the Hamiltonian of the system. If the Hamiltonian has no time dependence, then I can do this, and this piece is what we call it as a time evolution operator. So, the nature of the time evolution operator, as I was saying, the time evolution operator is denoted by the letter u, takes a state vector from t naught to t, and you can write psi of t as formally as u of t comma t naught and psi of t0. Why is norm time independent? Suppose you take the states to be a stationary state, suppose. What happens? This evolution operator, when you put on the ket, when you put it on the dual of this ket, you will put it as a u dagger, right? Complex conjugate and transpose, or the adjoint of this u operator. Is this Hermitian? Is u equal to u dagger? What is Hermitian? Hamiltonian is Hermitian. Hamiltonian is the one which is Hermitian. U is not equal to u dagger, but u dagger is identity. Okay. So, this is the beauty, that u t comma t naught operating on psi of t naught, we call this as psi of t. I want to write what is psi of t. I would have written this as psi of t naught u dagger of t comma t naught. So, the inner product of psi of t with psi of t is same as psi of t naught with u dagger t comma t naught, u of t comma t naught, psi of t naught, right? And u dagger or u dagger u is going to be identity. Why? Because Hermitian, Hamiltonian is Hermitian. So, e to the minus I h t by h cross into e to the power of plus I h t by h cross. Is that right? This one is e to the plus I h t minus t naught by h cross. This will be e to the I, this is a h operator, minus I h t t minus t naught by h cross. Suppose I had an operator H here and some other operator here. I don't know what to do, right? Like what I'm asking is, suppose I have e to the a and e to the b. In classical mechanics, you would have written this as e to the a plus b. Can you do that here? Can you do that here? So this one you have to meticulously write. Because why are we doing this? Why are we doing this? Order matters. Unlike in classical mechanics, you could have written AB, e to the a plus b. You can't do it here. You have to be careful. Okay. So, lot of things will happen. So, you will see there will be a 1 plus a plus b, plus then you will also have a squared b plus b squared a, and so on. So, a's will always be on the left side. Thank you. It is definitely not, if you had got a hat squared plus b hat squared plus ab plus ba, then probably you could have written the other one as a hat plus b hat the whole squared. So, it is not possible, right? You need to have some kind of an approximation and see what is the commutator of a with b, and then maybe there is a way of writing it. Okay, so these are things which you can play around and see what is happening. Question is, if AB commutator is a constant, then I think you can show that, let's call that constant as some number, some a or something. You can show this as e to the power of a plus b times e to the power of half of commutator of a with b. Do this expansion and check this out. Okay. I use this assumption that the commutator of a with b is a constant. What does that mean? This means that if I take commutator of a with b, what will that be? If AB commutator is a constant, it's a constant, so this will be 0. So you can play around with these commutators. If something is a constant, you will be able to simplify it. In such a case, you can simplify and get something like this. I am forgetting whether it is plus or minus, but you will figure it out. Okay. So this, I am not sure about the sign here. There may be a plus sign or a minus. Just check it. Okay. So these are things which, where the classical mechanics and the quantum mechanics differs, and you have to keep it in mind when you are doing your operator algebra. You shouldn't be like a machine. I know in classical mechanics and you cannot lift it. You have to make sure that quantum mechanics, the concerned quantities which I evaluate, if there are products of operators which are Hermitian, you have to try and write the Hermitian combinations of the products of operators and then only do the computation. Okay. So this is very, very important. So I have already showed for you that since it is the same operators, A and B are the same operators, there you can add it up. Okay. If the commutator of A and B is 0, then also you can add it up. This is what I was trying to show in the previous slide, right. So UU dagger is always identity. So and what is that property which you have all seen? These operators are called unitary operators, right. Unitary matrices are such that complex conjugate and transpose multiplied by the matrix is identity. So what do I want to do here? I want to reproduce your familiar Schrodinger equation in the wave function formalism, which you did, you have done it many times, from this approach, where we have postulated how the time evolution of the state ket vector happens. Okay. So, how do you go to the wave function formalism? We did this. This thing is the one which is involving the integral over the position with the outer product of the position states. That is an identity operator. This integral dx, x with x is an identity operating on the same. So, left hand side is same as right hand side, because this is an identity. And we had also defined how to write the wave function. Here you can also write the time dependent wave function as the inner product of x with psi of t. Since Hamiltonian is dependent on p, we are working for a free particle. So, the Hamiltonian is dependent on p. I do not know what is p squared on x, but I definitely know what is p squared on p hat squared on a p naught state will be p naught squared eigenvalue times p naught. Right. Hamiltonian is p squared over 2m. So, we wrote the state psi of t in position space, but you could have written it in the momentum space. Right. So, that will give you the Hamiltonian when you operate h on psi of t. You can take the integral of dp outside. This will be h on p. And what will I call the inner product of p with psi of t? So, this is a Fourier transform of your wave function, psi tilde of p t. So, we will call this as psi tilde of p t, and h on p for p equal to the p squared over 2m will give you just a eigenvalue. So, this is just a dummy variable. If you want, you can put a p prime, p prime, p prime, and then you can use the fact that h hat on p prime is p prime squared over 2m on p prime. It is an eigenvalue equation in the momentum space. If you had done it in the position space, we do not know p squared on 2m on x, what it is we do not know. We need to find out. But here in the momentum space, it becomes very simple to write it as an eigenvalue. Since the Hamiltonian is dependent on B, it is convenient to work in momentum space basis instead of working in position space. So, convenience depends on the situation. So, which basis you choose and how to go from one basis to another, all these things we did for a finite 2-dimensional linear vector space. We can do it even for the infinite dimensional countable, uncountable, where you can define how to go from one to the other, or you can directly take an identity operator in the momentum basis, because the Hamiltonian states will be eigenstates of the momentum basis. What is the momentum basis? The same like your position basis. I am doing it in one dimension. So, this is an identity operator, and because it is a continuum, inner product of p with p prime should be a Dirac delta function, and we can write the arbitrary psi of t as dp. There should be a p, there is a dp and then a p outer product. Okay. And psi tilde, as I said, is this inner product of the state psi with p, which we call it as just to make contact later with the Fourier transform, we call it as a Seidel. If we operate Hamiltonian on position basis, suppose we have potential energies which are dependent only on position, which is what we see in the harmonic oscillator, and we operate it on a position basis state. Let's take an x0 state. Then this becomes, we don't know what is p hat operator on x0, but we definitely know that v, which depends on a position operator, will pull out the eigenvalue, which is again a function. The same functional form will be there. This also you have tried in one of the tutorial sheet, right? If the eigenvalue equation of x operator on x0 is x0 times x0, any function of x operator will give you the same functional form of x0. Recall? So I have just written. So p with x0, the question is still remaining, what is p with x0? There are various ways in which you can proceed. You can insert an identity operator in the momentum space, take the inner product of the momentum with position. All these things we can start doing and figure it out how the p operator will be done. So that is what we are going to do now. So we will essentially show, you have all read that the p operator is px operator. Is that right? We are going to prove this. We want to derive this. We want to derive that the px operator can be written as, in the position basis, as a differential operator with these right signs for the IH cross. So let us go over the proof. And why do you want to do that? Why do we want to do that? It is because we have to evaluate this piece. If we write a differential operator representation here, it would have given me del squared by del x squared with a minus h cross squared. Where are we heading? We are going to head to the familiar Schrodinger equation. We want to see that. But for that, we need to formally we should be able to say what this is in a systematic fashion rather than just taking the postulate as minus IH cross del by. So momentum operator, let us do some trick. So take two positions x1 and x2, x0, and in between the operator is a commutator of xp. What is this? Commutator of xp is IH cross identity operator. Identity operator will not do anything to the states. You can pull it out and write an inner product of x0 with x1. What is inter product of x0 with x1? That is your Dirac delta function. That is the definition of your position basis. So IH cross Dirac delta function. This commutator xp, you expand first. If you expand the commutator, it is xp operator minus px operator. So depending on the order, either the x will operate on x0 or x will operate on x1. Is that right? What is this value going to be? This is going to be x on x0 is x0. That is an eigenvalue, right, with x0 p operator x1 minus this x with x1 will be minus x1 x0 p operator x1. This extreme left hits the x0, extreme right operator hits the x1. So the second term already has a minus sign. So this is what you will get. simplify this, it is x naught minus x1 matrix element of P operator in the position basis. Steps clear to you? So this is the result we have to use for the commutator, and let us look at the simplified equation here. The commutator will be simplified as x naught minus x1 times the matrix element of the momentum operator between x naught and x1, and the right hand side is nothing but your Dirac delta function. Now from here, if you take x naught and x1 to be really close, it is like 1 over x naught minus x1 delta function. What is that 1 over x naught minus x1 times the delta function? You have to check, it will be a derivative of a Dirac delta function. What is the derivative of a Dirac delta function? Delta of x naught minus x1 by x naught minus x1 is nothing but a derivative of a Dirac delta function. So what have we shown here? From here, the matrix element of the momentum operator in the position basis is nothing but minus IH cross del by del x naught on x naught x1. So this is what we are showing. So now from here, what is the meaning of this left hand side to the extreme right hand side? The momentum operator can be given address in the position basis, a representation in the position basis as a differential operator. So I can put this momentum operator as minus IH cross del by del x operator, and the del by del x operator, when it hits x naught, it will give you del by del x naught. Is that clear? So this is all we are trying to say. So this implies momentum operator, it implies this top equation. Momentum operator is minus IH cross del by del x, and if this operator Px operates on x naught, then it will give you minus IH cross del by del x naught. What will that be? Now this is an eigenvalue equation. Eigenvalue is a differential operator here. It is a differential operator on the states. It picks the x1 differential operator at x equal to x1. Okay, whereas this side I could write it as minus IH cross del by del x as a operator. When it hits on like x naught, it will give me minus IH cross. So we have given a position representation for the momentum operator, which is a differential operator. Similarly, can you give a momentum representation for the position operator? Can use the same arguments and do it instead of x naught, x1, p naught and p1. Redo the same exercise for the matrix element of the position operator in the momentum basis, and show that it will have one plus sign IH cross. That is also seen because if you do a commutator bracket, there will be a relative sign. And please show that x on p naught is IH cross del by del p naught of. So that tells us that, so do a similar exercise for the position operator on p naught and verify whether this is satisfied. What I did for the momentum operator, now redo it for the position operator and convince yourself that it is again a differential operator. Differential operator involves a momentum coordinates. In general, you could write for any state psi of t. So earlier we had x0 and x1. x1 can be replaced by any arbitrary state psi, doesn't really matter. And you can show that the differential operator p, if you take the del by del x operator, it can hit the left ket and give you a del by del x0 times this. What is this? Position space wave function at x0 t. So I have given you a couple of pieces here and there, and now with this data, what is the next step? Take the time evolution operator or the equation which dictates the time evolution of a ket psi, which is h on psi, and take the projection onto a specific position in 3 dimensions or 1 dimension. In 3 dimension you take an r vector and we can write it this way. So now this is the exercise for you. H operator is p squared over 2m plus v of r, let's take, and p squared over 2m can be replaced as minus ih cross del squared by 2m. So let's redo this and then. So let me do it in 1 dimension. Let's come back to. So this piece is your time evolution equation and you take the projection to a specific x. I can still take the del by del t operator outside, doesn't matter, and say x of psi t. It is the same because del by del t only will hit the psi of t. X is not dependent on time. Similarly, here it will be x. If suppose we had it to be a free particle, p squared over 2m on psi of t. Suppose we will also do v of x later. If you want, let's write the v of x also. What is wrong? The p has a position representation which is ih minus ih cross del by del x in 1 dimension. So you can rewrite this as minus or ih cross squared by 2m del squared by del x squared. More precisely, maybe I can take an x0 here just to make it more dramatic with x0 psi of t plus this term v of x. V of x will give you v of x0 will be a number multiplying x0 with psi of t. So what is this x0 with psi of t? That's the wave function. So this equation I can write it as ih cross del by del t psi of x0 t equal to, what about this? Minus h cross squared over 2m del squared by del x0 squared psi of x0 t plus v of x0 psi of x0. What is this? This is your familiar Schrodinger equation in the wave function formalism. I postulated an equation for evolution of the state vectors. I tried to systematically write my momentum operator using a position representation which became a differential operator, and then the equation which we get for the wave function is exactly your time dependent Schrodinger equation. So this is what I am trying to say here, that you can do it even in 3 dimension and you can show that it is nothing but your time dependent Schrodinger equation. So del squared by del x0 squared will become a del squared operator, Laplacian. There are a lot of things which I said today which involve for you connections between classical and quantum mechanics, and then I went into the evolution equation. I gave you an evolution operator which is unitary, and then we slowly studied what should be the position representation for the momentum operator. Then I asked you to find what is the momentum representation for the position operator, and then I said you can, using these data, you can actually reproduce your wave function Schrodinger equation the time dependent shows. So I'll stop here.